Okay, so I also have your first homeworks, Deniz, Baran, up here, Khan, Muhammad, and Doğa. Okay, one of the common mistakes, it's common to, in fact, all students. There are two question types that I like, but they are kind of tricky to ask. One is to ask the student to prove something, prove that such and such, because in such a case, most of the time, what the students does is that they make all the arguments, and sometimes even arguments contrary to what they are trying to prove, and the last sentence is, hence we prove that this is the result. The second tricky question is to ask the student to show something in two different ways, and even if the two different methods would not agree, their last comment is always, so the two approaches are consistent. So that is what you lost in your first question. The two approaches, they are inconsistent. They are consistent with each other with a suitable interpretation. You get different results. And the difference is the normalization. If you normalize both of the results, then they are consistent with each other. But in the perturbative expansion, we don't impose this normalization condition. The condition that we impose in this perturbative approach is that the corrections should be orthogonal to the unperturbed state. And this is not consistent with normalization. Now, another problem was the third question. At least there was one of you who made a mistake. Now, you see, this is our Hamiltonian. Epsilon 1, epsilon 2, epsilon 1, epsilon 1, epsilon 2, delta, 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 which we wrote as H0 plus H prime, and H0 is equal to epsilon 1, epsilon 1, epsilon 2, 0, 0, this one. And H prime is equal to the remaining part. Now, there is a degeneracy over here, but the degenerate states are the first and the second states. These are the 1, 0, 0 state and the 0, 1, 0 state. These are the degenerate states. So if you just restrict your H prime to this 2 by 2 subspace, your H prime is just 0, delta, delta, 0. So this is what you need to diagonalize first. And if you diagonalize this, you will see that the eigenvectors are 1 over square root of 2, 1 plus or minus 1, and the corresponding eigenvalues, they are plus or minus delta. So in this new basis, that's how we change our basis. This is 1 over square root of 2, 1, minus 1, 0. 1 over square root of 2, 1, plus 1, 0. And 0, 0, 1. This is kind of our new basis, the good basis. Let's call this one psi 1, psi 2, and psi 3. The shift in the energy of the first state is equal to psi 1 H prime psi 1. This is minus delta. The shift in the energy of the second state, this is psi 2 H prime psi 2. This is plus delta. And the shift in the energy of the third state is psi 3 H prime psi 3. This is just 0. Psi 3 doesn't shift at first order in perturbation. So this E psi 1 is actually the new ground state. So there's a single one. Psi2 is no longer the ground state. Now, any questions? And then, of course, once you identify the new ground state, what should be the correction to the ground state? So, if you, the correction to the psi1, the first order correction, would be just psi1, h prime, psi2, now psi3. That is the only state that it can couple to. That has a, well, this is the general expression. Let's say k psi k divided by e k minus e1 summed over k different than 1. But of course, due to our choice of the basis states, k equal to 2 also doesn't contribute. The only thing remaining is the k equal to 3 term. And that just gives this is equal to delta over epsilon 2 minus epsilon 1 times psi 3. This is the first order correction to the ground state wave function. Now the second question, this is question 3. Well, the second question was kind of trivial in the sense that we are looking for this. We are studying this system to d squared by dx1 squared plus minus h bar squared d squared by dx2 squared plus v of x1 x2 times psi x1 x2. Yeah, most of you got this question correct. This should be equal to e times psi x1 x2. But we are also told that we are considering fermions. So that tells us that psi x1 x1 this is equal to 0. So the Dirac delta x1 minus x2 psi x1 and x2, this is in fact 0. Well, actually, the potential is not really there. I mean, the fermions do not feel this potential at all. So there's no correction to the energy, no correction to the wave function. Well, you have actually calculated the first order corrections. And A turned out to be 0. In fact, any order, the corrections would be 0.
Why does the fermion doesn't feel?
Well, you see, the potential we choose, this is equal to lambda Dirac delta x1 minus x2. This is a potential that the particles feel only when they are at the same point. Unless there's spin, they cannot be, or any other quantum number, they cannot be at the same point. So basically, they don't feel it. Now, in the first question, some of the mistakes that you had was, okay, most of you were saying that let's look at the eigenstates in this form, psi 1 cosine theta 1 0. Now let me just say 1 and 2 plus sine theta 2 and psi 2. This was minus sine theta 1 plus cosine theta 2. Okay, this is some of you, and in the class also we were looking for the eigenstates in this form, and you had shown that theta is proportional to delta over epsilon 1 minus epsilon 2. Now, up to delta squared terms, sine theta is just delta over epsilon 1 minus epsilon. Sine theta is just theta, which is delta over epsilon 1 minus epsilon 2, but cosine theta is not equal to 1. The cosine theta is 1 minus theta squared over 2, which is, we have the 1 minus some factor times delta squared over epsilon 1 minus epsilon 2 squared. Paran, right? Okay. So there's a delta squared correction over here. Not in theta. If you calculate theta, receives the next correction to theta is delta cube, which we are ignoring, but up to delta squared, cosine theta also is not 1. Okay, any questions about any of the materials, anything that you want discussed? I mean, this week I would rather review what we had done up to now, and I would rather continue discussing based on your questions. Okay, we can go over the homework, but the second and the third homeworks also, but I would rather if you ask questions. Yes?
For the second question, we also expect to find some of the explicit wave functions.
Well, write something explicit. We have an explicit problem over here.
I said that phi1 and phi mb states.
You see, when you are asked what is the ground state, you can say Eg is the ground state. Well, that is true. But, find an explicit expression for that. One way that we make fun of the mathematicians is that one way that we make fun of mathematicians is that for you, saying that the solution exists most of the time is enough. But for us, no.
It's also really
Well, you see, all of this semester is basically about what happens if you cannot solve the Schrödinger equation. And we know the solution exists, but we cannot find it. Still, we cannot just give up. We have to do something.
In third question.
Okay.
In the first one, I thought I should diagonalize the whole matrix.
Yes. That's you. I didn't give your name, but
Yes. So we should only diagonalize the part and then put it back.
You see, what we are doing in degenerate perturbation theory is that you only look at the degenerate subspace. And then there is the Hamiltonian. Your Hamiltonian has some matrix representation in that finite dimensional subspace, and you diagonalize that one.
I thought probably it does work that way. If I choose a basis just for these two of them, then it might not be like a complete basis, the third one, for the whole space.
You see, if you just consider the mixture of any two states, they span the same space as long as they are independent.
Yes, yeah.
So they will be complete. You see, in this problem, a 3x3 matrix of this form, you can also diagonalize exactly. And I think there was at least one of you who made an exact diagonalization of this 3x3 matrix. But the idea is that, how to see how it works. Now, the third one is non-degenerate, so you forget about that. Oops. For that one, you can just use non-degenerate perturbation theory. We still have homework 2 after homework 1. No, not yet. I mean, I will probably finish reading it, the homework 2, until Friday. Homework 3 will be for next week.
For question 2, question 1 in homework 1.
Okay.
You didn't get the tan, you just used the cosine and sine and you expanded both separately, so that's how you got the squared.
True.
But if you get the tan, you don't get it.
If you don't?
You don't get the squared part.
In the perturbative expansion?
Yes.
True.
No, in the Taylor series.
No, in the Taylor series of cosine, I get the delta squared 1.
Yeah, but it's the cosine. But if you divide sine by cosine, you get tan. If you expand the
True,
tan,
true.
you then get the square.
True.
So when do you know when to use the tan or use the
Well,
cosine
you see,
and sine?
if you look at the perturbation theory, you don't get delta squared correction also. Right? So in perturbative expansion, perturbative result, for let's say psi 1 is 1 plus some factor times delta. 2 plus terms of the order of delta cube. This is the result of perturbation theory. Now, in exact result, up to delta squared corrections, psi 1 is equal to 1 minus some factor delta squared 1 plus delta 2 plus terms of the order of delta cube. So the idea is, okay, these two answers, they look different, but in fact they are the same. Up to terms of the order of delta cube. How to see that? If you just, for example, let's take psi 1 is equal to 1 minus delta squared. This is just a normalization. 1 plus some factor times delta. Well, 1 over this factor times delta would just give me 1 plus the same factor delta squared plus the other terms plus of the order of delta cube, which is 1 minus this normalization factor, 1 plus some factor times delta 2 plus terms of the order of delta cube. And up to a normalization, both answers are consistent with each other. Both answers are the same up to a normalization. It's not which one to use. I mean, whichever one you use, you will get the same answer up to corrections of the order of delta cube. Just use whichever one you want. They are the same.
Yeah, talking about the Taylor and the perturbation, right?
Yes. The exact, what I mean by the exact result is the Taylor expansion.
Yeah, I understand this part, but for the part of sine and cosine,
Okay.
here you expand them separately.
True.
I made tan and I expanded tan, so I didn't get the square. That's what I'm saying.
Oh, okay. So you started with the tan solution.
Yeah.
Why?
I don't know. It's not nice.
Okay, did I deduct any points from you?
No, I'm not
Okay.
asking about the points.
No, I mean,
just want to understand.
That's fine. I mean, use whatever you want. Both of them are correct as long as you are consistent. In the sense that, do you want to use normalized eigenstates? Then you cannot use the 10.
Why?
Because it's not normalized. Do you want to use states normalized to 1? It has advantages, but not using states normalized to 1, as you said, it looks nicer. You might prefer that. Then states will not be normalized to 1. And in that case, when you are talking about the averages or the probabilities, you have to be careful. Because when you are talking about the probabilities or averages, you have to divide by the normalization, which is no longer 1. But if you do everything properly, consistently, whether you normalize it to 1 or, I don't know, some 1 plus tangent squared or whatever you want, all of them are the same. Normalization doesn't make any shouldn't make any physical difference. It will be just how you interpret certain factors. It will be modified. Well, of course, if you started with the 10, I mean, this question didn't make too much sense for you because you get the same result. So you are not happy. You are not happy. Okay. Hmm? Okay.
I have a silly question for second one. I didn't understand what question 3 asks.
Which question 3?
The third one.
Oh, the third one
The
question.
you solved in the beginning of the lecture. First step, third question.
This one, the homework 1, third question.
The one you just solved.
Okay.
I didn't really understand what the question is asking you to do.
Okay, now, the thing is, this is a simple application of degenerate perturbation theory. So you see, if you look at each one of the questions, the first question is kind of standard perturbation theory applied to 2 by 2, an exactly solvable system. And just to see whether perturbation theory works or not, or how it works in a model that can be solved exactly. Question 2 is, well, it turned out to be kind of a stupid question when it was applied on fermions, but nevertheless, it gave you an idea of how to apply this perturbation theory in infinite Hilbert spaces. And question 3 was about a simple, in fact, it's also exactly solvable, a simple system in degenerate perturbation theory. And we know that in degenerate perturbation theory, the thing that we have to pay attention to is that we have to choose a basis. I mean, you see, the problem with the degenerate perturbation theory now, let's just say these are our basis states. And among this, I is equal to 1 to up to n are degenerate. So if these are degenerate, an alternative basis to using psi 1 up to psi n would be just to use, let's say, phi I. This is equal to aij psi j, I and j from 1 up to n. Just take any linear combination of these n states. They are still energy eigenstates of our unperturbed Hamiltonian. Let me put 2 zeros. So we have an infinitely many choice of bases in this case. Bases which are energy eigenstates of H0. So which one to choose? I mean, it would be nice if we could work with any one of them, if any basis would work. But the problem is, you see, the correction to the wave functions contain, let's say, to the case state is a sum of certain factors divided by En minus Ek. We have these differences in the energies in the denominator. So this tells me that I cannot really use any basis, because if I use any basis, in that case, since I have many states that have the energy Ek, many different states that have the energy Ek, then I would have 1 over zeros, which just doesn't make sense. I mean, perturbation theory, in fact, tells me that, I mean, I can use perturbation theory only if corrections are small. Now, one way to avoid this, I mean, in the numerator we have this factor. Now, we have this problem if the numerator is non-zero in the basis that we use for degenerate states. So the trick is to set the numerator to 0, to choose a basis, a suitable basis. You see, we have an infinitely many choices. And to choose one, basis for which the numerator, this matrix element, is 0. So that is what the trick is about. Now, let's do it more formally in the third question. So we have the Hamiltonian H0 was this one, or H prime is 0, 0, 0, delta, 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 delta. Now we have a degenerate basis. These states, the one state, let's say this is 1, 0, 0, and the two state, this is 0, 1, 0. These are degenerate. So let's form this matrix. Let's look at H prime 1, 1. And 1, 2, H prime 1, 2. Now this is 2. 2, H prime 1. 2, H prime 2. Now this states 1 and 2 is my degenerate states. So I form this matrix, which is 0, delta, delta, 0. And then I find some linear combinations of 1 and 2 whose matrix elements would give me 0. So, and this tells me that if instead of 1 and 2 I work with 1 plus 2, 1 over square root of 2, this which we called psi 2, and 1 minus 2, 1 over square root of 2, this we call psi 1. Now for these states, psi 1, H prime, psi 2, this is equal to 0. So if instead of this basis 1, 2, and 3, we would use psi 1, psi 2, and psi 3 as our basis, and then go ahead and calculate the corrections. Of course, psi 1 and psi 2 are still degenerate. So in the numerator for psi 1 and psi 2, I would get 0. But the numerator would also be 0. So I'm saved from my problem. So this is what the question 3 is about. So first find this good basis for which I don't have this problem of the degeneracies. H prime in the degenerate subspace is diagonal. So this is what I mean by the good basis. And then once you identify a good basis, the rest is just identical to non-degenerate perturbation theory, because you have resolved the problem that the degeneracy would cause. And then there was another tricky part, not so tricky, but once you introduce these delta terms, the degeneracy is lifted, you only have one ground state. Without this delta, you have two ground states, two degenerate ground states. With the delta, non-zero delta, it is lifted, so there's a single ground state now. Have you studied thermodynamics third law? The entropy at 0 temperature, 0 Kelvin, is 0. From a quantum mechanical perspective, you see the entropy, you will eventually define it as the number of accessible states, number of states that your system can be in. So if you put your system at 0 temperature, then your temperature will be in the ground state. So the third law of thermodynamics in a quantum mechanical description mainly states that the ground state should be unique. You cannot have degeneracies in the ground state. Now this is an example. Why the degeneracies are shifted? Well, if you have symmetries, quite often you will get degeneracies. For example, let's say if you have such a potential well, you can say that you would either have a solution which is localized in this around this minimum, or you might have a solution localized around this minimum. So you might expect to have two systems, two degenerate ground states. One is localized on the left, the other one would be localized on the right. But what happens is, I mean, we didn't discuss that in WKB in much detail, but there is a finite probability of tunneling from the left to the right. So if you call this state your first state, this is your second state, the Hamiltonian, ignoring tunneling effects, would be just diagonal. And in fact, it will be degenerate. But there is a finite probability that there will be a tunneling. The first state will be tunnel to the second state, or the second state will tunnel to the first state. And this H prime, which will be your perturbation, your tunnel transition probability between the two states, will have this form. Where delta, by the way, would be just, it is proportional to, let's say, 8 power minus pdx. It will be exponentially suppressed, but nevertheless it will be there. If this is the energy, the integral will be from x1 to x2. This is the tunneling probability, which will be proportional to your delta. And once you turn on the tunneling, as in this third question, then you don't have any degeneracies left. In quantum mechanics, the ground state will not be degenerate.
In this question, I don't understand just one thing. Like, even the tunneling probabilities, like everything should be symmetric, right?
Okay.
So why ground state energy is so?
Well, you see, you end up having two states. I mean, just back to this problem. You have 1 plus 2. This is one state, 1 over square root of 2. The other one is 1 minus 2. 1 over square root of 2. The tunneling probability is symmetric, the potential is symmetric. So your eigenstates should also be symmetric. So this is one eigenstate, and this is your other eigenstates. But they don't have to have the same energy. And in fact, it turns out that they don't have the same energy. Only one of them is the ground state. Other questions?
Not from the questions that's from right is like
Okay.
when you define the transition between A and B, you said it's the wave function A squared. Why would you choose that to be the transition between A and B?
Now, what we said was we assume that we have a wave function which, let's say, initially, which can be written as Ca t e to the power minus I over h bar e a of t a plus Cb of t e to the power minus I over h bar Eb of t times b. This is the general solution of the time-dependent Hamiltonian. Now, then the question is, what are you interested in? Would you like to, let's say, look at the probability of transition from the state A to the state B up to a time t? If this is what you want to determine, then you first create a state in A. So at t equal to 0, the state is in A. And then the probability that I will observe it in state B would just be Cb of t absolute squared. Or if you want to find the transition probability from B to A, then this will be Ca of t squared with the initial condition that Ca at t equal to 0, should be 0, and Cb at t equal to 0, this should be 1. So if I wrote something different...
No, you wrote that, I don't
Okay.
understand. Because I don't get why it's Cb or Ca.
So what do you understand from this transition probability from A to B?
The probability it will move from state A to state B.
Okay, so how do you measure it? How do you determine it? So to determine it, what you do is, I mean, forget about the photons. Let's just imagine we can measure the state directly. Now, if you are, let's say, throwing dice, you would just throw the dice. You take your dice initially. Now, in this case, we have a given state A, and we would like to look at the probability that it will make a transition to B. One thing we can do is we can just take, I don't know, let's say, hundreds of states A, and then wait until the time t, and measure how many of them are still in state A, how many of them are still in state B, right? So first we have to create all these states in state A, and none of them should be in state B. So that is what the initial conditions are about.
Yes.
Okay, then at time t, we look at the probabilities. How many of them are still in state A, how many of them are now in state B. Now the probabilities are nothing but the absolute squares of the coefficients of my states. Those are my probabilities. So that's why if I'm looking at the transition probability into state B, I just take the coefficient of state B at the time t. So it's basically CBT squared tells me what is the probability that I will observe my system in state B at the time t. And that is the probability I'm looking for.
What if you didn't initialize the state to be all in A?
Okay.
Would CB be the same at T?
Now, of course, if the initial conditions are different than CB and CA, they will also be different. But then I wouldn't have this interpretation. I wouldn't say the transition probability from A to B, but I would call it, I don't know, whatever my initial state is. Then I would say the transition probability from that state to B. But even that wouldn't make that much sense because my initial state, even my initial state has a probability of being in state B. I mean, if I want to calculate these probabilities, these are what the initial conditions I should choose. Of course, I'm free to choose whichever initial condition you like.
So the initial condition rules or governs what's the square of the coefficients represent physically.
True. Depending on your initial conditions, the coefficients will have different interpretations.
We have the initial condition CA 1 over 2, CB 1 over 2.
1 over square root of 2. Okay. Well, that would be something different.
So we have a different expression for PA to B.
Well, I mean, that wouldn't give me PA to B. Now, the expression for PAB is this one. If you choose some different initial condition, then the absolute squares of various coefficients will be different things, not PABs or PBA.
Are we talking about a one particle system?
One system. Well, I mean, the probability interpretation, you can also give it a statistical interpretation. Eventually, they lead to the same thing. I mean, we rarely can make measurements on a single state. You can either say that we are looking at a single system and these are the probabilities. But anyway, if you want to determine the probabilities, you have to make multiple copies of the same system. Or you can say that we have many particles and this is the fraction that we measure in state B. CBT squared would just give me the fraction that I will observe at the state B at time t.
Do you have an example in mind for the
For the
variational principle? Maybe you can.
well, we have the second homework. Yeah, I mean, we don't have much time left, so I would rather not go to the second homework. We will have time also on Friday. Yeah, it's kind of straightforward calculations, in the sense that the algorithm, let's say, for the variational principle, you make the initial guess, which depends on your parameters. How many you want. And then the matrix element, the expectation value of the Hamiltonian, in the state psi, and of course this will also depend on your parameters. And to determine A0, B0, C0, etc. Then the ground state energy is less than or equal to H psi A0, B0, C0. This is the basics of the variational principle. And the closer you get to the ground state, the closer your wave function will be to the ground state.
It's always exact when you choose the default one.
I mean, is it exact? In simple systems, you can find the exact ground state. Like, for example, the harmonic oscillator. We just tried this Gaussian wave function, which goes to 0 exponentially, and it gave us the exact ground state. And in the hydrogen atom, I mean, the easiest choice, at least for L equal to 0, would be, you can also choose a Gaussian. That's not the exact ground state. You can choose e to power minus r divided by some coefficient. That gives you the exact ground state. And I think that was your homework was the Gaussian. But if you also start with e to power minus alpha r, just a linear function in the exponential, you get the exact ground state. Now the thing is, if by changing these parameters you are able to reproduce the ground state, then this method will give you the ground state. But of course, for a general problem, if you don't know the ground state, you can never be really sure whether you have the ground state or not.
So, but if I try with different functions, then I could choose the one gives minimum, right?
Yes, sure. And for whatever function you choose, the minimum of the matrix element of H should be always larger than the ground state. You can try hundreds of different wave functions, and the one that gives you the smallest value would be a better prediction for the ground state energy. If one of them has the same form as the ground state, then you will reproduce the exact ground state. But again, you never know.
And you can judge whether it's close to the exact ground state by taking the inner product of our guess, which is minimum energy, and the exact ground state.
If you don't know the exact ground state, what to do? If you know the exact ground state, what's the point in using this one?
Educational purposes. I
Sure.
did something like that in
Sure.
the last question. Second.
Well, the nice thing about you can, of course, by increasing the number of parameters, you can just change the shape of your function arbitrarily, and you can actually get quite close to the ground state and the ground state wave function by using a trial wave function that has many parameters. But of course, it would be nicer if you just can find a suitable trial wave function by using some physical arguments and fewer parameters, some symmetry, some other physical arguments. And in the book there was this example of the hydrogen molecular ion, and well, just using a trial wave function with a single parameter, we could just reproduce the binding energy by a few electron volts with a single parameter, but using some physical arguments. By using more parameters, you can just get arbitrarily close to the ground state. Okay, so we can continue on Friday. And on Friday, if you bring questions, that is what I would prefer. If you don't, we can continue with the homework questions.